this person over there is another Code Dive record holder, and the person is Łukasz Langa, and his record is in the category of the shortest self-written biography. It only has 124 characters, so it's very, Twitter friendly. And let me read it to you. So Łukasz's self-written bio is this: Python committer since 2010, chronic perfectionist, pianist, dad. In his free time uses Python 3 to help Facebook move fast. And one thing that you want to know about Łukasz, especially for tomorrow, I guess, is that, well, he unsuccessfully tried to install Ruby on his machine. That was back in 2004. And after he gave up on the crashing installer, he typed Ruby alternative into Google. And this is how he discovered Python. So I guess this is more relevant for today and more relevant for tomorrow, is that Łukasz likes immersive role-playing games, jazz music, Scotch whiskey and burritos. He says not necessarily at the same time, but how about we challenge him tomorrow and, shove some burritos down his throat, followed by some good whiskey. Anyway, the title of the talk is the one you can't really miss. It is Thinking in Coroutines, and it is going to be performed by Łukasz Langa.
All right. Welcome. My name is Łukasz Langa. I come from the internet. You can find me in all sorts of places online. So if you have any questions further on, or any comments or whatnot, feel free to contact me. If you want to rant about Facebook, Python 3, type hints, analog synthesizers or whatnot, yeah, I'm your guy. So unless this wasn't clear enough, this is going to be a Python talk on a C++ conference. So I'm actually a bit anxious about this, and I'm interested how many of you are actually Python users? Can you raise your hands if you are? That's awesome. That's way more than I expected. So how many of you are already Async IO users? Good. Awesome. So right audience, because this is going to be an Async IO primer, so you should be all good after the talk, I hope. If you watched today's Rust talk about concurrency, some of the terms will sound familiar. Most of the time, they mean something else, sometimes in subtle ways, sometimes radically different. So just approach them with an open heart and try to understand them as fresh. This is not Rust, it's going to be different. So first of all, we're going to talk about why do we even want async programming? It doesn't read from top to bottom. It's a bit harder to understand what's going on. So why would we even bother? Isn't it worse than what we have? When I finally convince you that it is worth it, I'm going to actually give you a very sort of thorough top to bottom introduction, how does Async IO do this? How does Async IO solve the problem? And when you already know, we're gonna focus on how should you actually think about programming in Async IO such that it makes sort of mental sense for you. So these are the 3 parts of the talk. So why async? Well, where I come from, we love async because it just sort of fits our brains if you switch your mind enough to it. To the point where our Facebook.com application that we affectionately call dub, it's very heavily async. Everything that you do, from data fetching to decisions that you do on what story to show you, and actually choosing the right associations for the objects that we have for a query or whatnot. All of this is asynchronous. Without it, I don't think we could serve you Facebook for the number of users that we have today. But that's front end. On the back end, we actually use C++ very heavily. And then the Folly library that we open source is also very asynchronous friendly, and the async futures and whatnot are actually the basis of a lot of APIs at Facebook and outside of it. So asynchronous from front end to the back end as well. Even the other open source projects that we release very often have asynchronous APIs by default because they just sort of make sense for us. So okay, enough of the advertisement, like, but why? Like, why does it make sense? So the sort of 101 explanation is like, nobody likes to wait, right? So if you have multiple things that you need to do, and all of those are essentially asking questions to remote services, how about we ask all of them at the same time, right? If we do, the actual total time to wait is going to be shorter, and latency is going to be smaller, and like the user is going to be happier. Because the trick is, as we found out at Facebook, that it's the latency that drives the experience, not the total time that it takes to perform an action, right? So responsiveness is very important. This is why we have progress bars and whatnot, right? So how do you solve this? Well, traditionally people said, like, I know, just gonna spawn threads. It's gonna solve everything for me. We're gonna have like concurrency, parallelism, everything's gonna be just great. Well, in the world of Python, and maybe not even in the world of Python everywhere, that doesn't make much sense, like, if you just naively come like with this assumption, because there's problems. Asynchronous programming like has some of them, but not nearly quite like as many. Like with threading, you might have like, you know, debugging that is hard. You might have like hard sharing of state and whatnot. So like threading is not something that is easy for programmers to actually comprehend. Like, more importantly, if your application is very big, like actually, you know, proving whether it's gonna work fine or not is super hard. And yeah, and you need locks. You need locks, and like you better have enough of them, but not too many, because then like all of your wins from concurrency are gonna wane. But even if you just have one, you still can like deadlock if you don't re-enter like correctly or whatnot. So like all of this is actually very tricky. And better yet, in Python, that doesn't even win you anything, right? Like most of the time, like you're gonna use threading, you're gonna be very happy, and you're still going to see that it only utilizes one core of your blocks, and going to be very sad, and, you know, sort of like, oh my God, I need to rewrite everything in Go. So in Python, we have this global interpreter lock, which is a construct in the interpreter that protects the internal data structures when you're executing Python code. It is actually there, and it's it doesn't sound like very intuitive. It's there to make Python fast. It sounds strange, but it does, because if you just have one lock, you only have to acquire this one. If you had many fine-grained locks, that becomes like way more expensive, especially if you have a language like Python, which is reference counted, and the reference counts like happen all the time. But because of this, there's only one Python opcode executing at the same time. So unless you're waiting on I/O, there's not going to be much that you can do at the same time. So you end up with underutilized threads. This is very tricky, in fact, because it ends up causing problems which are subtle and hard to debug. Like, this is an image that I created just for a post that I did after fixing a bug at Facebook for a library that we use like in basically all of the Python programs that we write there. Like, the problem that we had with this library was that we experienced a CPU leak. And that just doesn't sound right. That just sounds like some voodoo, like, you know, saying. It's like, what is a CPU leak? Like, memory leaks, yeah, I can understand how that works. But CPU leak, what are you talking about? Well, the experience of people was that, like, as the same operation actually executed, like, you know, in time, becomes slower over time. Even though if you profile that operation, it doesn't do much. It does the same amount of work. But for some reason, it just becomes slower. We found out that somebody added a reporting functionality on a separate thread. It's the orange thread right here. And he didn't clean up his data structures just right. So his reporting was spending increasing amounts of time just to do like ascending over the network somewhere. So the operations that we really cared about, which are the blue and green threads, actually could execute, you know, in decreasing frequency. So the perceived problem was a CPU leak on those threads, but it wasn't them, it was the orange problem. So that's what the global interpreter lock gives you. And unfortunately, I think it's here to stay until 4.0. There's a project to actually remove it. And it's actually very easy to remove the global interpreter lock, but it's very hard to make it in a way that it is generally faster than it was before. So that's the challenge. This is why in Python, we actually focused totally on asynchronous programming to do anything that is non-trivial. So here comes async I/O. But before async I/O, there was twisted. That's late 20th century. like ancient history, like that predates like Guido van Rossum, the creator of the language, moving to the United States. That predates PEP 8 and unit test and the warnings framework in Python. Like Glyph Lefkowitz already came up with the idea that if you want to have performant Python, you just cannot, focus on threads. You have to do something else. So Twisted actually uses callbacks, sort of not unlike the, old JavaScript and whatnot. And it uses deferreds, which are sort of like futures. And it was very successful. It was a game changer in the asynchronous world of Python. The problem with it was that it is sort of very different as a programming paradigm. It's very unnatural for newcomers. So while it filled a niche, for a long time, it wasn't very mainstream, to be honest, and it is not to this day. Other people started actually writing very serious programs in Python, like massively multiplayer online games, and they just figured out that, again, that like threads are not going to cut it, and Twisted is not very user-friendly, right? Like they actually realized that the human mind sort of thinks imperatively, right? Like likes to think in imperatives, not in reactions. So they thought, like cooperative multitasking might be the solution, continuations, coroutines, and generators. They implemented it in a way where they switched the Python function stack from using the C stack to use something else, essentially a linked list. But the patch to do this in CPython was so big that it never got actually merged to CPython. So again, we had some niche, nice, but something that most people couldn't actually use. So 10 years passed. We were writing Django applications and like other stuff in the meantime. Python received iterators. It received simple generators that Tim Peters implemented, and they were always written in a way where they enabled, sort of constructs for later use for asynchronous programming. But it only took Greg Ewing to create PEP 380, which adds yield from some magic construct that actually like connected all the dots. And suddenly the craze of async programming was back for Python. And specifically async.io actually is a rewrite of Twisted essentials in a way that utilizes coroutines as a first-class construct. So let's get to code, right? Like I was talking for 10 minutes now, so like let's get more concrete. I'm using a bunch of. So actually, there's like colors on the slides. You cannot see them, I guess. Yeah, I'm going to show you code, and I'm going to show you outputs. All the code is in Python 3, obviously, because async.io uses syntactic constructs that are not available in Python 2. Don't worry about remembering all of this. At the end of the slides, there's going to be a link to the slides, so you don't have to like retype things that you find interesting now. But there's going to be more than just user code that we're going to look at, because async.io is in fact called a reference implementation, which means it is literally designed to be readable and grokkable, so you can go ahead and read the code to understand the concepts behind it. So we're going to look at the code to actually prove that, like, you can also understand how this is built and build your own maybe later. So, okay, without any more further ado, like, what does async.io do? Well, provides you an event loop that loops and calls callbacks. That's it. That's the most important slide on the deck. That's essentially what it does. Everything else is built on top of this concept that there's a loop that calls callbacks that you have scheduled. So in Python, you would actually start this. You would actually instantiate an event loop like this. You would just import async.io, get the event loop for the current thread, and run it forever. That's going to be a very boring program because it doesn't have any callbacks to run yet, but it already runs your event loop. That's already the building block. Like, this is what we have to do. This is the boilerplate. So what does it mean? What does run forever do? Like, is there an event loop? Like, is there a loop inside? Well, there is, right? Like, if you actually look at the implementation, it in fact has a while loop inside, and that while loop just runs once for a very long time unless we have some stop exception being raised. So run once looks for all scheduled callbacks, because it's not just like, callbacks that you schedule in a list. Like, sometimes it's event-based, right? So something like, I don't know, a file descriptor being ready or whatnot might trigger a callback to be ready by, right then. So we run once, and then execute the callbacks that apply, and rinse and repeat. That is all there is to it. So what does the loop call? You register callbacks by saying call soon or call later or whatever. Like, this is essentially the API. So if we have a plain old function called just anything, it just prints out a thing, like it's just very boring. We can tell the event loop that, hey, please call it soon. And call soon takes an optional argument saying how soon. Like in our case, it's going to be 1 second soon, 2 seconds, and 3 seconds. That doesn't mean exactly 1 second. That means at least 1 second later, at least 2 seconds later, at least 3 seconds later. Or we can just say call later, right? Like that we can also do. So we do all this. We schedule this, and we run it. If we do, it just runs our thing. We already can see sort of in the timing that, oh, it looks like it did it concurrently. That's cool. Like, don't treat this as a benchmark. I was like executed a long time ago on an old laptop. So like, yes, Python is slow, but not that slow. That's just to show you like the timings. So anyhow, like, we actually call the callback when time comes for it. We don't do busy looping, right? Because there's event programming. So depending on your operating system, you're either going to use the old POSIX select or something newer like KQ or EPOL. We also support Windows. So essentially what I'm trying to say is async.io abstracts away whatever your kernel provides or like your operating system provides. Works the same way. You just write one piece of code and it should run on our supported operating systems. I'm not going to say anywhere, but close enough. Yeah, so this assumes that every loop iteration is short, right? Like that anything is going to just take a very short amount of time and it's going to be great. Well, what if it's not short? What if it's actually very, slow? In this case, if you can already see the graph, like, next to the code, like, there's no magic. Like, one callback is executed after another, which means they're actually going to, take its time to execute and slow down everything that comes after. So anything 1 will take its time and slow down anything 2's execution, which in turn is going to slow down anything 3's execution. If we actually look at the output, this is exactly what's going to happen. So that's not great. This is not what we wanted. We wanted concurrency. We wanted to fix the issue and not make it worse. So how do we even discover that it is the case? Fortunately, if you let it, async.io will tell you that you have some callback that takes way too long to execute. All it takes is an environmental variable that you need to set with your execution, and then async.io is going to do a lot of noisy output for you to let you find a bug if you notice that your application is slowing down in certain places. But fundamentally, how do we actually not do this? How do we not block a single function? How do we make stuff run fast? So the answer is coroutines. We use coroutines, which from the user's perspective are not unlike plain old functions. So if we take the old function that we had, nothing crazy there, you just put async and await in the right places and you're done. So it looks like this. Now we have an async function. If you notice, it's no longer also time sleep, but it's async.io.sleep because we need to have non-blocking variants of everything that can actually take a long time. But essentially, it reads the same, which is way nicer than callback-based systems and stuff like this. So that's the entire point. Just a short, detour to just, specify terminology here. If you have the function that you defined, it's an async function. Easy, right? The coroutine is an effect of calling this function. So an async function is like a template, right? It's a factory of coroutines. It's like a class, right? When you call it, then you get a coroutine, right? It's like an object. This is important because if you see, you have this await thing. Await reacts to coroutines, but to make a coroutine, you just call an async function that returns coroutines. That's important also because you can pass the coroutines around. If you call an async function and you get a coroutine, you can do stuff with it. We're going to do stuff with it later. So this is why I do this distinction. Async function, coroutine. That makes it much easier to explain things later on. That's also true for the async.io provided async functions, right? Same thing. You have a thing in the async.io module. It's an async function. If you call it, you get a coroutine that you can await on later. So back to the function. We have a function. the async await syntax has not always been there, right? As I said, like, like the sort of resurrection of interest in async programming in Python came when Greg Ewing added yield from to the language. And in fact, the first implementation of async IO used a bunch of decorators and yield from. So you might still see every now and then, like, some code that does this. This is like arguably way less friendly, like doesn't read as obviously as yield, as await does. And also like it sort of confuses generators with coroutines. So don't use it for new code, but you might still find it on like Stack Overflow or some old code bases that you're gonna work with. So I need to tell you about this, but that's the past. Now you should focus on async await that reads much better, writes shorter, like everybody wins. So how do you actually put coroutines on the event loop? Like what do we do? Like, because we have this distinction, you have something that is async, and a normal Python program is not async, right? And even the callbacks that we called before, they were just simple functions. Fortunately, it's not that different, right? Instead of just saying call soon or call later, we just create tasks, and you put coroutines there, and it's happy. And now, for sure, in fact, like it ran concurrently while waiting, and everything was fine. Well, so how does that create task work? It actually says, it does what it says on the tin. Like it creates a task object, and that task object, holds the coroutine and executes it slowly. So let's look inside. Let's see what the code looks like for this. So the task class in async IO, like if you instantiate an object, it does some like boring assignments and whatever. But the important thing later on is that it simply says call soon. We already know call soon. It just does this. It just says call soon with a single step of my coroutine. And that's it. But hey, wait. What is a single step? Coroutines are based on generators. So a single step is going to be a single iteration of the loop. It's going to execute until the next await. So it does a single series of yields and throw to just see what happens next. And what can happen next is either the coroutine is done, it returned. So we're like, okay, we have a result. We can assign it, right? With the set result method. Or it didn't work out, like there was some exception. So we set the exception. Or nothing interesting happened. So we just say, call soon, again. And this is how this works. Like this entire concept is called a trampoline, right? When we execute a bit of code and then, just schedule ourselves back on the end of the queue. So this is how this looks. If we have multiple of those, like, Coro 1, Coro 2, Coro 3, they're going to just execute a single step, put themselves back on the loop. Coro 2 is going to do the same thing, put itself back on the loop. Coro 3, same thing. And they're going to leave the loop when they're already done, right? Like one way or another. But this is how that works. And unless you actually schedule for a specific time, this is a first in, first out thing, so it's fair scheduling. And now you know how async IO works. There's actually no more secrets. That is, in fact, exactly how that is done. But everybody lies, and I also sort of lied to you a bit. So before you have this thing where we're sleeping, right? And we're sleeping for 1 second, for 2 seconds, and for 3 seconds. Okay, that's obvious, but 2 seconds in, we're actually saying to the loop, stop. Like throw whatever you have and like let's leave. So in fact, async IO is not happy with you doing that because you left some things on the loop that will never get executed. You're calling loop stop, but there's still stuff scheduled on it. So it's going to tell you like, hey, man, like you actually left stuff undone. And what am I supposed to do with them? So instead of running forever and just sort of believing that everything is going to be fine, it would be great if we had a function that will just like run until a coroutine is complete. I wonder how we could name this function. Oh, run until complete, awesome. Like, so this is actually what you do. You just put a coroutine there and it's gonna run until it's complete. So yeah, let's do that. But we have multiple tasks. So the thing is, we actually had to wrap them in a way that like we can pass it to a single run until complete call. So there's another coroutine called async IO wait that accepts like an iterable of tasks, like a list. So we create this list, pass it to async IO wait, and now No more lies. Like, let's be honest with ourselves. Like, that just works. That does whatever we want it. Now it's really concurrent. We have no warnings. It for sure runs everything until completion. But how do we really know? We don't know because we didn't actually print anything later on. So fortunately, coroutines can also return things, right? Like, so far the example was very artificial. We didn't actually return anything from our coroutine, but we can. So let's, for example, add like an invocation of like daytime now. Let's return it, whatever. This is then stored in the result of a task, and we can get it back. So after actually adding just those 2 lines, which is essentially, yeah, let's print the result, and let's return it in the coroutine, it's going to look like this. Like, first of all, everything is concurrent, so like the starts of the functions are going to be like executed very quickly, but then the returns from the functions are going to come depending on how much we slept in the body of the function. In fact, if we only waited on a single thing, then we can just use the result that run to the complete directly returns. That's sort of like an easier API if you just have one thing that you waited on. In fact, if we only create one task, we don't have to call loop.createTask. We can just pass the coroutine directly to run until complete, and it's going to do the correct thing. So if you have coroutines, they can also have like stuff that didn't work out, like there was an exception raised. For example, in our particular problem, we passed the wrong type, right? This is fortunately stored in an exception field, so we can get it back and like see what happened or what went wrong. So on the execution, we would see that there's a type error, unsupported operand type, like that comes from the insides of async.io sleep, how this is implemented. But if you would want to actually catch this before it bubbles up through our control code, we can just wrap the thing that can error out in a try except. There's nothing special about it. If you just await on a thing, you can wrap the await and see what happens. So in this case, like, we would recover, we wouldn't have an ugly exception. There would be, just some maybe a bit strange output. So to sum up, we can invoke coroutines like this. If you're outside of a coroutine, so you're still in the blocking world of like regular Python, you need to create a task, and you need to run until complete. If you are inside a coroutine, you can still create a task. What does that mean then? That just means I want the event loop to execute this at some point, but I don't really care when. But if you await, that means I need to wait until this is complete, and the coroutine is not going to execute any further until that thing is done. In the case of create task, we're just going to carry on, right? We can still like go on task and see whether it's done or not. But unless we await, we're just going to go on with our lives. So this is it. These are the basics of async.io, and it actually provides a lot of things. I'm going to go through them pretty quickly because it's like, it's not going to read documentation to you, but it provides a lot of the typical building blocks that you would expect from an asynchronous framework like this. So you have creating connections, like that supports like IPv4, IPv6, which is very important for Facebook, like TCP, UDP, Unix socket. So all of the basic things that you would expect they're there, like supports SSL like very easily. So like that is also like super nice and pluggable. Can resolve domain names asynchronously, so that was a biggie. You can also listen to connections, so you can write servers. Same thing, supports TCP and Unix sockets, support SSL. UDP is supported by the same datagram endpoint as the client because you don't really have connections, but like it works, like as you would expect. These are like low-level APIs, but there's even more low-level APIs for like socket mangling if you want to do this. So for example, you can watch file descriptors like directly. Unix pipes are supported as well, so you can do like crazy IPC and whatnot, signal handling, stuff like this. A very often like overlooked thing that is like super cool in async.io is subprocess handling. I think it's in fact like one of the nicest APIs that we have for subprocessing like in Python. So even if you don't do any I/O, like, but you subprocess a lot, like I would still use async.io for that because you can then wait and communicate with multiple processes at the same time, like without using threads and like other crazy things. So I/O stream handling is there, everything is there. So pretty much what I'm trying to say is if you want to actually do something, like you should just look at the documentation first. If you really miss deadlocks, you can still have them. No, I'm kidding. Like obviously, like synchronization primitives are very important, like in all sorts of algorithms. So they're provided, but most of the time I would just direct you to those queues. This is how you solve like a lot of the hard to understand problems otherwise. That's a model that is way more natural, at least in my brain. But nobody actually wants to implement everything from scratch. Like you would want to have something more like high level. So what's the Django for async IO? It's called AIO HTTP, which maybe is a stupid name because HTTP sort of suggests that it's very low level. It's not. It's a pretty comprehensive framework that does a lot of things. So I would suggest you look at this if you do anything webby. It's actually pretty well maintained and pretty active in development. If you use databases, I presume you do, AIOPG is the thing to do. You don't want to really use MySQL unless you're Facebook and you have like already a big investment in it. But if you do, there's also AIO MySQL. If you see the pattern, a lot of AIO libraries are going to be named like this, AIO something. Yeah, one that is not is UV loop. So the reference implementation is cool. You can look inside, like you can debug things very nicely, see why is this thing happening and how can I actually fix it. But what that means is like async IO isn't very performant like by default, especially if you like toggle all the debug switches. So what UV loop does is it provides an alternative implementation of the event loop, which is based on libuv, which Node.js is built on top of. I know that this doesn't quite sound like an endorsement, but it is. Like libuv is actually a very good piece of software. So UV loop, actually pretty cool. I would recommend it like very highly. We use it as well. So these are like sort of hand-wavy things that you have that you should look at. But one thing that I wanted to actually explain is executors. So it would be great if you have everything that is non-blocking and everything supports awaiting and you have the world that is fully asynchronous. But what if you have a thing that you just don't control, right? You have an anything function that some third-party library provides to you. It is using time.sleep or whatever else, but you cannot change it. It's not in your power to change it. Fortunately, with thread pool executors, you can very cleanly run things in an executor, which essentially means like, yeah, this code is blocking, so we're going to spawn like a bunch of threads or maybe processes and run them there. So for a lot of things, that is actually enough to just have a thread pool because the blocking comes from I/O, and I/O is already actually freeing the GIL on separate threads in Python. So that should be enough to unblock your main thing in async IO to do its asynchronous operations. So even in this case, like, you're going to see that, oh, here, does the correct thing. It's not quite as fast as it was before, but like if you need to deal with blocking code and there's nothing you can do otherwise, this is how you would do it. And in fact, we have two available executors. The first is thread pool, the other is process pool. So threads are obviously lightweight processes, or they're going to be with less overhead, but you're still vulnerable to the global contributor lock, which I think I already sort of scared you about enough. But that means that you actually have access to any memory that you have in the process. So any object in Python that you have, including modules and other very strange things, you can pass as arguments. It just works just fine. In the process pool executor, you are literally spawning a different process. So you have to pass your arguments around. So first of all, that means not all arguments can be nicely pickable, so like serialized to pass between processes. But that also means if your arguments are really humongous, you're going to spend a lot of time like just pickling and unpickling those things between processes, which sort of defeats the purpose. So you need to sort of decide like which ones are better suited for your case. Like I like process pool executors better because they're actually solving more of the problems that people in fact have when they need an executor. So this is what async IO provides. Like you're done with the 101. So how should you think about this? Like how can you actually just know where to put awaits and how to actually make this actually work? So what I found at first was that a lot of people confuse concurrency and parallelism. So let's just look at those first. So concurrency is about dealing with many things at the same time. like I/O, right? So we have waiting for many processes or handling many web requests all at the same time. Whereas parallelism is about doing many things at the same time, like compressing MP3s or rendering 3D animation frames at the same time. So these are different, right? Because if you have concurrency, you just mean that there's going to be many requests coming to me at the same time, but I don't actually have to deal with them right at the same time. Parallelism is actually about executing computation right at the exact same time. So async I/O solves concurrency. It doesn't, at least, at all help with parallelism. This is not its point. So to give you an example, like how actually async I/O can help us, let's ask Armin. Hey, Armin, what do you think about Python? Oh, it's 2016 and there's still no sensible way to switch Flake 8, which is the Python linter, between Python 2 and Python 3 mode. Yeah, he rants a lot. Like, he's a very smart guy, though. So he's right. In fact, like if you run the linter, it tells you all sorts of stuff that is wrong with your code. So let's run it over a file that we have. We have Flake 8. We run it, and it tells us, you know, some function is too complex, some line is too long. Like, it doesn't matter, right? It's like, you know, shit warnings. But now we have a syntax error. Like, no, it executes. Like, how can it be a syntax error? And then you look inside, and it's an async def. Of course. Flake 8 was running on Python 2, so it didn't understand that there's async defs. So you run another one, Flake 8 on Python 3, and it returns totally different errors. So you're like, oh, okay. So people at my company and me too, like we're gonna write code that is either Python 2 or Python 3. So we need a script that wraps both and runs both, right? Like one after the other. But that means now, like the time you wait for linting is twice as long, and a lot of the messages are duplicated because, like, as you see, like the version option is too complex and line too long. These are the same. So that's not great. Like, if only we had a system that lets us run sub-processes concurrently. So we do have one, right? So let's wrap what async I/O already provides. So we have a run coroutine that we're gonna, a run async function that we're gonna use later. So we create a sub-process, just like in the regular sub-process module. It looks like it's very many lines because I couldn't fit it on the slide, but like it's essentially just a one call. And then we wait for the communicate. We only use async I/O wait for because we want a timeout, right? Because that's sensible. Like we don't want the linter to just spend forever. And then when we have a return code, we use it. If timeout was reached, we can just kill the guy and like then wait until we see that like the sub-process actually is dead, and we can move on. So this is great. If you look, you probably also saw the pre-exec function thing. You know, there's a thing. Yeah, so I actually encourage you to do this. What this is essentially telling on pre-exec that, hey, if your parent is dead, the kernel should kill you too. It only works on Linux, but like that solves a lot of the problems with runaway children and whatever. So also the terminology is very disturbing, but I don't know. So again, don't write it down. Like this is going to be on the slides that I'm going to give you the link later on. So when you already have our run function that we're going to use, let's just spawn linters. So if you saw before, we used a list for our task, but now I'm using a dictionary. Why? Well, I like dictionaries because I want to know names of my tasks and address them by name when I'm returning errors. If something timed out, I want to know which one if there's many of them, right? Which is why I use dictionaries, but any data structure would be fine. And then you just wait on multiples of them, just like we did in our stupid toy example before. And it actually does all of it for us, right? Then the result actually holds the return code and starter out and starter error as the run async function that we designed. And this is it, right? The thing that I want to stress here is that you should always set timeouts for things. Like forever is not a term that should apply to computer science, right? Like there's no such thing as forever. So a timeout on wait for raises timeout error, while on wait, it only gives you back control. So then you need to actually check, like, are all tasks done? So you should always check if your tasks are done. If you don't, again, async.io will yell at you. It's going to say, you didn't actually, gather the exceptions or the results of the tasks that were done. It's going to be unhappy with this. So cancel tasks that aren't done if you're actually stopping the loop or whatever. Like that way, async.io was going to understand that you don't care about those tasks anymore. Yeah, so deduplicating messages like that I leave as an exercise for you later. It's actually pretty trivial compared to what we did just now. So if you treat all of this now as a building block, because we're not done yet, let's paint it green, okay? So we achieved concurrency. We already do a lot, but we can go one step further. And we can actually lint files concurrently if you have many of them. So now we actually see how async.io is nice and composable, because we can do actually tremendous amounts of things at the same time, right? We don't actually execute them directly at the same time. We just deal with the subprocesses. The subprocesses could be network connections or could be whatever else. But the point is, we can write a very simple program that composes, and now you can actually kill your box and utilize all the cores that you have. So coming back to what we described before, you have a very simple event loop that runs things one after the other. Right? It doesn't wait stupidly, it uses select or whatever else you have, but essentially it won't call more than one thing at a time. So concurrency is on a single thread of execution, which means for the most part you only need a single thread, and then you can still just totally maximize what you need to do. But what if you actually are doing CPU-heavy things and you have so many cores in your new server and you actually want to use them? Well, in this case, in the Python world, you just run multiple copies of your thing. That does exactly what you want, and that way you can actually utilize all of your threads. And since async.io helps you maximize a single one, that way you solve the entire problem. So it's 40 minutes into the talk, and we're sort of already done. So I have some bonus content for you. So first of all, you might have noticed that I didn't even say explain how futures work before. This is why. This is because I find that they are actually very confusing if you start out with them. Because futures are all those things that make Twisted fail to become popular. It's callbacks and everything. It's not very easy. But you might actually find them every now and then. So I'm going to just show you how they work. But they are actually not at all necessary for you to be successful in using async.io. And I actually don't want you to just think that, oh, this is a thing that I need to know now. It's nice for you to know how it works, and maybe in some places it's going to be very useful for you to communicate between coroutines or whatnot. But otherwise, this is not a block that is exposed for you to be used day to day. That being said, I think they're very easy. So futures. They're just objects. You can create them. And even if you create an object, it doesn't even have any state, just that loop that it's using. So we have this simple object that will hold a result in the future, but it doesn't yet. It holds nothing for now. So how do we know if it already holds a result of some kind? We can ask it, right? We can ask it are you done? And it's going to tell us true or false. Or we can say, are you canceled? Because maybe it's done, but it doesn't mean it has a result, but somebody said, I don't care, I'm not waiting anymore. So if you received a future from somebody, from some code, you can check if it's done like this. But on the other end, if you're creating a future for somebody, you can set the result using those functions. You might recognize them because actually the task that I showed you before is actually using exactly those building blocks, right? Tasks are sort of subclasses of futures. So if you're creating a future for somebody else, you can either set a result, or you can set an exception if something went wrong, or you can just cancel a thing. And finally, if you already know that something is done, you can ask for the result. When you do that, it's going to return you a thing, or maybe it's going to raise an exception. And when it does, that exception might mean that somebody set the exception, or it might mean that somebody canceled the thing, or it might mean that you actually called to get the result, but it's not done yet. So that function actually, if that's okay by you, you can just get the result right there. if you actually want to know if that exception that you're going to get is specifically because there was an exception that happened, you might ask for an exception directly. And if there was one that somebody set with set exception, you're going to get it back. If there was no exception, everything went fine, and the function is done, and the feature is done, you're going to get none. There was no exception, everything is okay. But if the feature is not done, or it was canceled, you're going to still get an exception raised out of this method. All right, and finally, polling for things is sort of stupid. So you can just add callbacks to like being notified that, oh, a thing is done. And the nice thing about the callbacks here is that they're actually going to be registered to be executed on the event loop using call soon, like everything else. So that actually composes really well. And if your callback is too slow, the event loop is going to tell you, and everything else applies. Like it's exactly the same thing. So with this in mind, this is how the feature works. Now we can introduce this concept of awaitable. So essentially, what can you await on? Well, you can await on coroutines. We explained them at length. You can await on features directly, which sometimes it's very handy, and the syntax for it is just beautiful. And finally, you can await on any object that implements a magic dunder await method. So let's introduce some more advanced async concepts that you're going to see, and you should actually use them as well, like async context managers. If you're actually not like a Python pro in the room, and like you're like, what the hell are context managers? They're a very simple piece of syntax in Python that solves a lot of resource management problems. You just say with a context manager as a name, which sort of nicely encapsulates things that you need to do before you get that object, and also things that you need to do when you actually leave that context. So the opening and closing files, opening and closing connections, or any other resource, really. So this is how this is implemented. Like Python likes magic methods, and here you have dunder enter and dunder exit to just sort of put functionality there when you create a connection, for example, or you disconnect. But when I'm telling you about connections, like you should already be like a little worried that, hey, what if getting that connection is actually taking time? It's a TCP thing. I need to resolve DNS. I need to do a lot of things, and that enter thing is going to block. Worse yet, if my dunder exit has some flushing of data being written over the network, that again can block. So using a regular context manager in Async IO might actually be very clunky. It's going to slow everything down, which is why we have async context managers. Those are implemented differently. They have specific enter and exit async functions. So with those, everything is back to normal now. Like async with is going to await like on those two events, and everything is nice and concurrent for you again. Same deal applies to asynchronous iterators. So in Python, you can iterate on things. Like this is like one of the most prevalent idioms of Python. Like if I were to choose like the number one, it would probably be this. So you can iterate on things. In fact, an iterator is a very simple construct. It's just an object that provides a dunder next method. Not all things are iterators, but they can still be iterable if they provide an iter method, in which case either they can return a different object, or sometimes they just return self. Like I can iterate on myself, I'm fine. So these are the two concepts, iterators and iterables. So again, like if you have a dunder next that does some network connectivity, for example, actually fetches the next row from the database or whatnot, that would block, that would suck for us. So we have asynchronous iterators, and those actually solve the problem very nicely. You might notice that iter actually isn't a coroutine, because typically it doesn't matter, right? It's just creating an object and just returning it for you. It's the dunder next that does the network connectivity or whatnot. So one of them is a coroutine and the other isn't. The reason why they're different is this, async generators. We also have those. And like iter couldn't be a generator, but that's a detail. Like the reason why async generators were added is this: if you have a nice asynchronous iterator that you wrote, That like looks a bit scary, right? It's a lot of code. What this does, it's a ticker. It yields numbers from 0 to 2 every delay seconds. Okay, cool, but that actually is a lot of code for a stupid iterator like this. With async generators, exactly the same functionality is provided by just 4 lines, right? Like, and that actually reads very naturally. You can just see like, oh, for I in range, I just yield and then I sleep. Okay, that's obvious. So in Python 3.6, you can do that. So from 13 lines, we went down to 4, and it's 2 times faster. So you should use those guys. Finally, random advice. You should use Python 3.6 because it's faster, debugging is much better, garbage collection is much better as well. Executors recognize dying processes, which like before that was pretty clowny. Like if some worker was killed, like Python would seriously not know. So now it's fixed. You can use async generators. So pretty much like if you're using Python 3 already, there's no reason for you not to use 3.6. And if you don't use Python 3 yet, you should switch totally. I'm going to be your mom for a second now, so just bear with me, but you should seriously write unit tests. Like in async programming, like it's actually very tricky to see the entire state of the program and like find bugs like this. So it's way easier to write a unit test. But because the event loop composes so nicely and you can just fire it up for just a single coroutine and then see was there anything left on the event loop, you know, and like how long did it take to execute and whatnot. Async IO is actually very easy to unit test. So do it. Like, you know, you can mock out things that you don't want very easily. So you can just run until complete with a single thing that you want to test. So I would totally recommend you doing that. I already showed you how you can debug with the environment variable. Like if you forgot, like this is how it looks like. You just set up Python async IO debug equals 1, and then you can have a lot of additional output that Python is going to provide for you. But if this is not enough for you, you can set up your application to be even more verbose. Like you can set up logging like for async IO to even internally, like debug you, print you out debug messages, and you can even show like uncollectible objects in the garbage collection. This is important because very often if you're doing something stupid with your coroutines, like you, for example, forgot to await or whatnot, you're going to see that this object is there. So that's helpful. And then set debug is essentially the same as the environment variable. So if you want to have some like remote way to trigger this, like this is how you would do it in your program. Finally, like setting signal handlers, that's actually pretty cool also for debugging, but you should do it always because like people are going to Control-C your application. They're going to send you like other sorts of signals. So you want to know about this. That can be as easy as just like calling loop stop, but you can do whatever in those signal handlers. So that, for example, helps to discover issues like this. If you just call a thing that happened to be an async function, now you already know, right, that what it does is it creates a coroutine. And then it drops it on the floor because there was no await. You forgot to await on a thing. So with all this set up, like Python is going to tell you, like unfortunately it's going to tell you at the very end of your program that, hey, you had a async function and you never awaited on it. But that's very helpful. Like at first, like people tend to forget to await. And then like if you're really a pro in Python, like there was enough like, you know, hands raised that like probably like there are some of you that actually wrote their own iterators or whatnot. Don't use stop iteration for generators. This is how we wrote this in Python 2. Like, you know, if you're done with that generator, you raise. But that's like, that doesn't compose it async IO. You're going to have very, very crazy errors if you do this. So instead, do this a bit nicer syntax, which is if I'm done, I return. And that also works for async generators, so do this. Prefer process pool executors. They solve more issues. Read the docs, because they're pretty comprehensive. Like, they might not be very beginner-friendly, but I hope this talk was. And if not, like, there's more resources about async IO. But they're at least pretty comprehensive. Like, you should actually find the thing that you want to, like, that you're looking for there. And I think I convinced you to at least look at the source. It's not very cryptic. It is designed to be a reference implementation for you to look at. So yeah, that's pretty much it. But does anybody use async IO? Is it production ready? Well, we have quite a bit of code in it. And if you release Facebook.com, which we do like 10 times per day, we cannot really copy over the new package to all the servers because we have like hundreds of thousands of them now. So what we do instead is we use BitTorrent, so that servers can sort of send, the new version themselves. And that piece of software is in fact Async.io. So without Python 3.6, you couldn't release a new version of Facebook anymore. So yes, it is production ready. That's growing pretty fast. And Instagram is also Python 3 now, and it's using Async.io increasingly and at a very fast rate. So that's also growing. So if your question was like, is this still experimental and provisional? No, it's not. You can use it. It's pretty, I wouldn't say hardened, but it's pretty battle tested by now. So I'm done, but before I'm done, I have a talk tomorrow about typing. So if you don't know what that's about, Python was traditionally very easy to use, beginner friendly. My 9-year-old actually has successfully written Python code in his life already. So yeah, that's cool. But if you have a very large application, sometimes it's very hard to figure out like, what did the author mean with this argument? Or what does that function return? So this is where type hints come in. I'm going to talk about them tomorrow. So in our case, if you have a function like this, what does it do? Well, you don't really know. Is command line a list? Is it a string? Or what sort of unit is timeout in? And finally, what does that return? What does that function return? So if we had type hints, we would know all this. It would be very obvious for us. So it's like, oh yeah, that's a list of strings. There's seconds in the timeout. There's a tuple that returns the return code, I guess, and the standard out and standard error. But what are the seconds in standard out, standard error? Like, there's no types like this. Well, you can just apply aliases so that it's actually very readable, because that's the point one of type hints, to be readable by humans. All right, I'm done. I used images, so I need to credit those guys here. And I have slides. So, okay, if I have any questions, I'm happy to answer them now.
Thank you very much, Łukasz. There are no questions on the website.
All right.
Are there any questions from the room by any chance? Don't be shy, just raise your hand and you will have a chance to ask a question. Maybe you can ask them a question.
I already asked a bunch of questions at the beginning, so I guess I'm happy with the answers. A lot of more Python programmers than expected.
So if I may, I'd like to just remind everybody that Łukasz's second talk will take place tomorrow in room 8 at 2:55. And with this, I think we owe Łukasz a big hand and to say thank you with a lot of applause. Łukasz Langa.
All right.